Good morning, my dear students. Today we are going to discuss one more important topic of class 12, that is electric flux. It is very important to understand what is electric flux because very soon we are going to start Gauss law. In order to understand Gauss law, first we should know what is electric flux. Electric flux basically involves two important quantities. One is intensity of electric field, another one is area. As you all know, intensity of electric field is a vector quantity. It has direction as well as magnitude. And area is also a vector quantity. In my previous video only I have explained why area is a vector quantity. Those who have not seen my previous video, they can go to YouTube search and they can search by typing area vector Swapnil Sajane. You are going to get an idea why area is a vector quantity. Now we shall start electric flux in detail. Electric flux is basically the total number of electric field lines passing through a cross-sectional area. It is called as electric flux. In order to understand in a better way, consider an example. It's a general example. Consider you are sitting in a room. This is your house and you are sitting inside. Okay. Since this is summer, you may feel hot inside. Therefore, what you do is you open the window. This is window, a large window. Okay. It has two portions or two doors. Okay. You open window. And the air is coming outside, from outside to inside. Okay. Consider this is A. You can call it as air lines. Air lines. Okay, these are air lines, just air lines. To understand in an easy way, I have considered air as air lines. Okay, you open first window. This window you open. Okay, and air rushes from outside to inside. Okay, from this area, air will enter. Okay, from outside to inside, and you may feel a little cold. Okay, because this amount of air is entering inside. Okay, and again you start to feel a little hot. What you do, you open this window also. Okay, and if you open this window also, the air will come inside this way. It means the amount of air entering from outside to inside is depending on two factors. First factor, it is depending on quantity of air. Quantity of air. If quantity of air outside is more, then more air can enter. And it is depending on second point, that is size of the window. Size of window. It means if window size is bigger, then more amount of air will enter. If window size is smaller, then very small amount of air will enter. It means the amount of air you experience by sitting inside the room, it is depending on two factors. One factor is quantity of air outside. Okay, if more air is there outside, then only air can enter into the room. Otherwise, if less air is there, then you experience less air inside. And it is also depending on size of the window. Size of the window or area of the window. Area of the window. Okay. In the same way, electric flux is also discussed. Okay. Look at here. These are electric field lines. As there are air lines, here electric field lines. Okay, according to our definition, the total number of electric field lines passing through a cross-sectional area is there. Okay, these are electric field lines, and we shall consider one area here. This is area. Okay, one more small area you will consider. This is small area. Okay, and again one more electric field. Okay, see here, as you can observe, here electric field lines are in more dense. It means the crowded electric field lines are there, therefore it is stronger electric field. Stronger electric field. And here the density of field lines is less, therefore we can call it as weaker electric field. Two types of electric fields are there. One is strong electric field, another one is weak electric field. Here I have considered one area. Let us call it as area A. Okay. And same amount of area I will consider here. Same amount of area. This is also area A. Okay. Here area is same in both the case, but electric field is different. It means the number of field lines linked with this area and number of field lines linked with this area. Area is same, but the linking of electric field lines is different. Here more number of electric field lines are linked. Here less number of electric field lines are linked. Okay, this is first point. Second point, here I have considered small area and here large area. Area is small, therefore number of field lines are linked less. Area is more, therefore number of field lines are linked more. Understood my point? Therefore, in this case electric flux is more. Electric flux is more because more electric field lines are linked. In this case electric flux is less because number of field lines are less. Linked are less. And in this case once again electric flux is less because area is small. Therefore electric flux is indicated by pi, and electric flux is directly proportional to what? Electric field intensity. If more electric field intensity is there, then more electric flux will be there. If less electric field lines are there or less electric field is there, then flux is less. And also electric flux is directly proportional to area. Okay, so by combining these two I can write electric flux is equal to E and A. Okay, as you know electric field is a vector quantity, area is also vector quantity, and the electric flux is not only depending on these two factors, it is also depending one more quantity, and that is angle between E and A. Okay, for example, see here. These are electric field lines. Okay, these are electric field lines, and I will consider area this way. Okay, and this is area vector. Okay, this is electric field and this is area vector. Okay, and how much is the angle between A and A? It is theta is equal to 0 degree. This plane is perpendicular. This plane is perpendicular to the electric field, but area vector and electric field are at 0 degree. Okay, therefore maximum number of electric field lines are touching here, linking here, and one more case. These are electric field lines. This is the direction of electric field, and I will place area this way. Okay, this is area and this is area vector. Okay, how much is the angle? Theta is equal to 90 degree. Okay, it means this area is parallel to the electric field, and this area vector is perpendicular to the electric field. Okay, both are acceptable. Here no electric field line is linked with this surface. No electric field line is linked. Here maximum number of electric field lines are linked. For 0 degree maximum result and for 90 degree minimum result, which trigonometric function can give? It is cos theta. Okay, therefore along with electric field intensity and area vector, flux is also depending on what? Cos theta. Understood? Therefore I can write it as pi is equal to E A cos theta, where theta is angle between E and A. Okay, or since theta is there, cos theta is there, therefore I can write it as vector E dot vector A. This is vector form of flux. This is vector form of flux, and this is magnitude form of flux. Okay, and some important points here. Note, dot product of two vectors always results a scalar quantity, therefore flux is scalar quantity. Flux is scalar quantity. Dot product of two vectors always results a scalar quantity. Cross product of two vectors always results a vector quantity. For example, torque is equal to force into displacement. Force is a vector quantity, displacement is a vector quantity. Force into displacement gives you what? Torque, where torque is what? Vector quantity. And work is equal to force into displacement. Force into displacement. Okay, force is once again vector quantity, displacement is once again vector quantity, but dot product of these two gives what? Work, where work is what? Scalar quantity. Similarly, dot product of E and A gives you what? Flux, and flux is scalar quantity. Second point, unit. See here, E is there. E means what? Electric field. Electric field is equal to force divided by charge. Force experienced by unit charge, and that is called as what? Newton per coulomb. And here area is meter square or Newton meter square per coulomb. And third point, dimensions. E and A is there. Okay, E and A. Okay, E can be written as force divided by Q, and area. Force is F is equal to M into A. M is mass and A is acceleration. Therefore, it is M L T to the power minus 2. Area is length. Therefore, it is L square. And Q is what? Charge. Charge is equal to what? Charge Q, or I is equal to Q divided by T. Flow of charge per second is called as what? Current. Therefore, Q is equal to I into T. I is current and T is time. Therefore, I can write it as ampere, because unit of current is ampere and T is T. Therefore, it is M L cube T to the power minus 2 minus 1 minus 3, and it is A to the power minus 1. This is the dimension. M to the power 1, L to the power 3, T to the power minus 3, A to the power minus 1. Okay, these are the dimensions of electric flux. Okay, so one more important point, flux is equal to EA cos theta. Okay, this is the formula for electric flux. If the area is uneven, uneven means like this, okay, then the formula is going to be, see, this is electric field lines. Okay, you can observe here, these are the directions of electric field lines. Okay, if I consider this area, the whole surface or whole area is how much? A. Whole area is A. And if I consider very small area, let us call it as dA. Okay, dA. This for this area, this will be area vector. Okay, area vector is always perpendicular to the surface. For open surface, it is outward. Okay, for open surface, it is perpendicular, actually perpendicular to the surface. For closed surface, it is outward normal. Okay, and for this small dA area, this is area vector. And you can observe here, there is an angle between area vector and electric field, and that angle is theta. Okay, if I consider this area, small area, very small area, let us call it as dA only. Okay, and for this dA area, this is the direction of electric area vector, and this is the direction of electric field. And you can observe here, theta is angle, here theta angle, here theta angle, both the angles are different. If I consider this area, very small area, once again dA, and this is the area vector. Okay, and area vector and electric field, in this case these two are in same line. Okay, if I consider this area, and this is the direction of electric field, sorry, area vector, and this is the direction of electric field, here angle is different. It means in these all situations there is a different angle is there. Okay, in such case what we are supposed to do is we have to add all these DAs. We have to consider very small areas, DA. Then if we integrate all those DA areas, we are going to get total area. Understood? So for this small area DA, the electric flux will be d pi flux for DA area, E into dA. Okay, if we want to calculate all the electric field, all the electric flux, then we are supposed to integrate it, and integration of d pi is what? Pi is equal to E into dA. Okay, this is the formula for flux. Okay, this is for uneven surface. Okay, so this is all about electric flux. Okay, now let us begin Gauss law. Gauss law is applicable for any closed surface, okay, irrespective of its shape and size. Because in our previous videos we have discussed about different kinds of charge distribution. Okay, linear charge distribution we have discussed, volume charge distribution, surface charge distribution. In all such type of distribution we can apply Gauss law in order to calculate electric field. Okay, Gauss law is applicable, or Gauss law is used to find out the electric field also. Okay, for different type of charge distribution, because in previous videos we have discussed different types of charge distribution: line charge distribution, volume charge distribution, and areal charge or surface charge distribution. In all such cases we can calculate electric field with the help of Gauss law very easily. Okay, first let us start with its statement of Gauss law. The total electric flux linked with any closed surface in free space is equal to 1 divided by epsilon naught times the charge enclosed by the surface. Okay, according to this statement I can write pi is what? Flux, electric flux is equal to Q divided by epsilon naught. Okay, this Q is what? It is quantity of charge, net charge within the surface, or sum of all charges. It is sum of all charges enclosed within the surface. And this pi is what? It is total electric flux. This Gauss law can be applied, okay, for any closed surface irrespective of its shape and size. It can be applied for any closed surface, whatever the shape and size. Okay, and one more important point, this Q charge is within the enclosed surface, I mean within the surface. Okay, or charges located outside the surface, they do not make any contribution to the electric flux. Okay, that is second point. The charges outside the surface do not contribute to the total electric flux. Okay, And see here, pi is equal to q divided by epsilon naught is there, and I can write it as pi. Pi is what? Flux, and flux we know, closed integral E into dA is equal to q divided by epsilon naught. E into dA, it is what? It is flux. Okay, flux formula. And here I have taken closed integral. It is not line integral. Closed integral I have considered because this Gauss law we are applying for closed surfaces. Okay, this is closed. Okay, and this is the formula. Okay, and for any closed surface, if we consider only single charge, the net flux is going to be q divided by epsilon naught. For example, if I consider a sphere, okay, if I place a charge here, the total number of flux or the net flux is going to be pi is equal to q divided by epsilon naught, because only single charge is there, and these are what? Electric field lines. Okay, and here we can consider area vector. This is area vector. Okay, this is what? Electric field, and this is area vector. Area vector. If I consider this area, this is area vector, and this is electric field. Therefore, the total flux is q divided by epsilon. If I consider triangle, okay, and I place a charge here, then the total flux linked is going to be pi is equal to q divided by epsilon. Or if I consider a cube, okay, if I consider a cube, and if I place a charge, single charge, then the flux linked is going to be pi is equal to q divided by epsilon. No need to calculate. Directly we can come to the conclusion that pi is equal to q divided by epsilon if we place only single charge in a closed surface. Okay. And for distribution of charge, we are not going to apply the same method. Okay, we have to calculate with the help of Gauss law, and let us start. Okay, but before we could calculate the electric flux for different charge distribution, we should know some of the important conditions. Okay, important conditions. First point, electric field. See here, this Gauss law is containing E and dA. Therefore, electric field should be symmetric. Symmetric means it has to be same, or it has to be constant. Second one, the angle between, because here E dA, it is in vector form actually. If I write in magnitude form, E dA cos theta. Okay, theta is angle between E and A. The angle between electric field intensity and area vector. Area vector must be same. And the third point, the charge distribution. Charge distribution should be symmetric. Should be symmetric. Okay. If all these points are valid, then we can easily calculate the electric flux. Okay. And now, if all these conditions are satisfied, then that surface is also called as Gaussian surface. Gaussian surface. Okay. Gaussian surface, it is just an imaginary surface. Okay, in order to help us to find out the electric flux or electric field. Okay. Now let us discuss the proof of Gauss law. Proof of Gauss law. For this we shall consider a small charge q plus q. If it is plus q, then the direction of electric field lines will be radially outward, like this. Okay, and for this we shall consider a Gaussian surface in the form of sphere. Okay, so this is Gaussian surface. Okay. And you can observe here, okay, this is the direction of electric field E, and if I consider very small area dA, the total area is A. If I consider very small area dA, then the direction of dA is normal to this surface. Okay, and this is the direction of A. The angle between electric field and area vector, both are same. I mean it is 0 degree. If I consider this area, small area, okay, dA, and you can observe once again the angle between electric field and area vector is 0. If I consider at this location dA area, then the direction of electric field and area vector is same. If I consider this area, once again same, electric field and area vector angle is same. Then I can call it as Gaussian surface. Gaussian surface. Okay, and here magnitude of electric field, the magnitude of electric field is given by E is equal to 1 divided by 4 pi epsilon naught Q divided by R square. If I consider this area, this distance as R, then R distance is constant, therefore it is R square. Okay, ideally outward. Since positive charge is there, then therefore the direction is radially outward. The direction of electric field is radially outward. Okay, and the total flux pi is equal to what? It is closed integral E into dA cos theta. Since theta angle is how much? It is 0 degree, therefore cos 0 is 1. Therefore it is E into dA. Since electric field is a constant, in this situation electric field is constant, we can take it as outside, closed integral dA. Okay, E closed integral dA. dA is what? dA are these small areas. If I add all these areas, then I am going to get sphere. It means closed integral dA is total area of this sphere. It means 4 pi R square. And E electric field I have calculated it as 1 divided by 4 pi epsilon naught Q divided by R square into 4 pi R square. Here R square is cancelled, 4 pi is cancelled. What is remaining? Q divided by epsilon naught. This is flux. This is the proof of Gauss law. Gauss law. Okay. So this is proof of Gauss law. Now we shall start the applications of Gauss law. Applications are very important in theory examinations. Many a times the questions have been appearing. Applications of Gauss law. And the first application is electric field due to infinitely long straight charged wire. Its length is how much? Infinity. Okay, for this consider a charged wire. Okay, there are n number of charges. This type of distribution of charge is called as line charge distribution. Okay, the total length of the conductor is how much? Wire is how much? L. Okay, if we are asked to find electric field at a point P, located at a distance of r from the line charge distribution. Okay, the first point is we are supposed to consider one Gaussian surface, and there are certain conditions in order to consider Gaussian surface. The first condition is it has to be closed, and second condition, the angle between E and A must be same and the distance has to be same. Okay, these are the conditions, and we shall choose cylinder as a Gaussian surface in this case. Okay, and the axis of cylinder has to lie on this line charge distribution. Okay, in such way we shall consider cylinder. This is cylinder, closed cylinder actually. Okay, and here you can see the distribution of charge will be like this. It is radially outward. Okay, for one charge the direction of electric field lines will be like this. For the below charge the electric field lines will be like this. For below charge the radially outward the direction of electric field lines will be like this. Okay, first point I will write here only. First point, charge distribution is linear charge distribution. Linear charge distribution. Okay, and we shall consider one, in such a case we shall consider one parameter, and that will be lambda. Lambda is what? Linear charge density. Linear charge density. What is linear charge density? Charge per unit length. Charge per unit length is called as what? It is lambda. Okay, since the total length is L, it is infinite, therefore we have defined one term, that is lambda. Lambda is linear charge density. Okay, and you can observe here this cylinder is considering two plane surfaces, one curved surfaces. If this is the cylinder, then this is plane, top surface is plane, bottom surface is plane, and one curved surface is there. Totally three surfaces are there, and in these three surfaces you can observe here electric field lines will be radially outward this way. If I consider this as a curved surface, then electric field line will pass normal to the surface. It means this is the direction of electric field. In curved surface I am speaking. If I consider this very small area, then this is the direction of electric field. The direction of electric field and the direction of electric area vector both are same. It means the angle is 0 degree here. If I consider this area, very small area dA, the area vector and the electric field line once again acting in same line. It means you choose any point in curved surface, the angle between electric field and area vector is going to be same. It is 0 degree. If I consider plane surface, as you know, the direction of electric field, the direction of area vector is always perpendicular to the surface. Then this is the direction of area vector, and electric field will be once again radially outward. Okay, this is the electric field, this is the area vector. The angle is how much? 90 degree. You choose any point in a bottom plane. Okay, you are going to get a 90 degree angle between electric field and area vector. You choose any top surface or top plane, once again the area vector and electric field, the angle will be 90 degree. Okay, totally three surfaces are there, two plane surfaces, top and bottom, one curved surface. In at any point in curved surface, the angle between electric field and area vector is 0 degree, and at any point in a plane surface, the angle between area vector and electric field is 90 degree. Understood? Okay, and we have chosen Gaussian surface in what shape? Second point, Gaussian surface. What is the shape of Gaussian surface in this problem? It is cylinder. A Gaussian surface in the shape of cylinder with radius how much? R. Okay, radius R, and whose axis lies on line charge distribution. In such a way, we have considered cylinder as a Gaussian surface. Now, according to Gauss law, from Gauss law, closed integral E dA is equal to Q divided by epsilon naught. This is the Gauss law. First, we shall consider LHS part. LHS, that is closed integral E dA is equal to, the cylinder is consisting three surfaces actually, two planes and one curved. Okay, we shall add all the three in order to get the total flux. This is E dA cos theta. This is for top surface or top plane, and second one integration E dA cos theta. Once again, this is bottom, and third one E dA cos theta. This is curved surface. As you can observe here, the angle between electric field and area vector in curved surface is 0 degree. In top and bottom surface it is 90 degree. Therefore, cos theta, cos 90 and cos 90 here. Cos 90, it is 0. 0 into anything is 0. Therefore, closed integral E dA is equal to, for curved surface it is E dA cos theta is cos 0 and cos 0 is 1. What is common? What is constant? E is constant, integration dA. Okay. E electric field and integration of dA. It means if I add all these dAs of curved surface, I am going to get what? The area of total length L, that is 2 pi r into L, where 2 pi r is what? Circumference, and circumference of one circle actually, and L is what? Length. This is circumference of one circle, this is circumference of one circle, circumference of one circle. If I add all the circumference, I am going to till how much? L length. I am going to get what? 2 pi r into L, that is area. Okay, this is, let us call it as equation 1 and it as equation 2. Okay, and RHS part, that is charge within the surface. Charge within surface. Inside this cylinder, how many charges are there? There are n number of charges are there, but we have defined the number of charges actually, and that definition is what? Lambda. Lambda is equal to linear charge density. Lambda is equal to charge per unit length. It means the total number of charges in L length is how much? Lambda into L. Lambda into, or Q divided by epsilon naught, and Q is equal to what? Lambda into L divided by epsilon naught. This is what? Equation 3. Okay, and from equation 2 and 3 I can substitute in equation 1. In LHS part, E into dA, in place of E into dA I can write E into 2 pi RL. Putting 2 and 3 in 1. Okay, I will write here. Putting 2 and 3 in 1. E into 2 pi r into L is equal to, and RHS is lambda into L divided by epsilon naught, where L is cancelled and E is equal to lambda divided by 2 pi epsilon naught into R, where electric field is inversely proportional to R. It means as distance increases, electric field go on decreasing. Okay, and the direction of electric field is perpendicular to the curved surface. Direction perpendicular to the curved surface. Okay, so this is all about electric field due to infinitely long straight charged wire. Okay, you can note down. Okay, let us start second application of Gauss law. Second application, electric field due to infinitely charged surface. Infinitely charged surface. It means we have to consider one surface. This is not a small surface actually. Okay, this is a huge surface. Its surface is infinite actually. Okay, and there are charges located here, and the direction will be radially outward. Radially outward means like this. Okay, and backside also, here also. Okay, and in order to calculate electric field with the help of Gauss law, the first point is we have to consider what? One Gaussian surface. Okay, if we are asked to find out electric field intensity at a point P, okay, at a distance of r from the plane of paper or plane of charged sheet, okay, then we have to use Gauss law. But for the Gauss law, we have to consider one Gaussian surface. And in such situation, what shape we are going to consider as a Gaussian surface? Okay, once again we shall consider a cylinder only. Okay, I will redraw this diagram. These are the charges. We have to consider Gaussian surface, and Gaussian surface we have to consider in the shape of cylinder only. This is cylinder. Okay, and this distance is how much? This distance is r. Okay, and let us call it as point P. We are supposed to find out electric field intensity at point P, located at a distance of r from the plane of the sheet containing charges. Okay, and we have to consider the shape of cylinder in such a way that this cylinder should have same distance. Okay, in this side also, in this side also. This distance is also how much? R distance. Okay, and the total length of the cylinder is how much? R plus R, it is 2R. Okay, and as you can observe once again, here two planes are there. This is one plane, this is one plane. Okay, two planes are there and one curved surface is there. Okay, if this is the cylinder, then this is curved surface, and here these are plane surfaces. Okay, so first point, charge distribution is what? Surface charge distribution. Surface charge distribution. And for surface charge distribution, we have considered what? We have defined already one term, that is sigma. Sigma is what? Surface charge density. Surface charge density. It means charge per unit surface. Sigma is equal to Q divided by A. Okay, where A is what? Area. And Gaussian surface. Gaussian surface. What is the shape of Gaussian surface? Cylinder having length how much? 2R. 2R, and passing normal to the plane sheet of charges. Passing normal means perpendicularly it is passing. For example, if this is the plane, then the cylinder is passing this way. Okay. Okay, next point. As you can observe here, the direction of electric field will be radially outward. For example, if this is the plane sheet, infinite plane sheet, then the direction of electric field will be like this. Okay, and I have considered cylinder in this way. Okay, and the direction of electric field and one plane surface. Okay, if this is the plane, I mean this plane, then the direction of electric field will be like this. Okay, for one plane, the direction of area vector at this plane and the direction of electric field, they are at how much angle? They are at 0 degree. Okay, for curved surface the angle will be 0 degree. Sorry, for a plane surface the angle will be 0 degree, and for curved surface you can observe here, for curved surface, okay, if I consider this area, then this is the area vector, but the direction of electric field line will be like this. It means the angle between electric field and area vector is how much? 90 degree. At this point the direction of area vector and electric field is 90 degree. This is area vector and this is electric field. It is 0 degree actually. And at this point the direction of electric field and area vector, the angle is how much? 90 degree. For if you choose any point on the curved surface, you are going to get 90 degree. If you choose any point of these two plane surface, you are going to get 0 degree angle. If I consider this plane, then this is the direction of electric field and this is the direction of area vector. Both are lying in same point. Therefore, angle is how much? 0 degree. Understood? Okay. Once again, from Gauss law. Gauss law. What is Gauss law? Closed integral E dA is equal to Q divided by epsilon. Call it as equation 1. Okay. Once again, in this situation, how many planes, how many surfaces are there? 3 surfaces are there. Surface 1, surface 2 and curved surface. 3 surfaces are there. Okay. Therefore, LHS part, closed integral E dA is equal to closed integral, open integral E dA cos theta plus E dA cos theta plus E dA cos theta. This is for first plane, this is for second plane, this is for third plane, that is curved plane. Okay. For curved plane you can observe the angle is how much? For curved plane, if this is curved plane, you can observe here the direction of electric field is in this direction actually, and area vector will be like this. Okay. If this is curved surface and this is the area vector and this is the direction of electric field, they are at how much angle? They are 90 degree. Okay. And for curved surface, if I consider this as curved, angle is 90, therefore cos 90 is 0, 0 into anything is 0, therefore this value cancels. Okay. And electric field is a constant taken outside into dA, theta is 0 degree, and once again it is E into dA. For these two, angle is how much? You can call it as plane 1 and this is plane 2. This is actually plane 2 and this is plane 1, and this is what actually curved. Okay. And it is 2E into dA. Okay. This dA is what? Actually A. Okay. Because this cylinder you have considered, it has area how much? A. Area of the cylinder is how much? A. So this is LHS part. E into dA is equal to this much. Let us call it as equation 2. Next, RHS part, that is charge within the cylinder or charge within the surface, is equal to how much it is? Q divided by epsilon naught. But Q is what? Charge. For the total number of charges we have defined it as how much? Q is equal to sigma into A. So it is sigma A divided by epsilon naught. Call it as equation 3. Putting 2 and 3 in 1. Therefore, we are going to get 2EA is equal to sigma A divided by epsilon naught. A is cancelled. Therefore, E is equal to sigma divided by 2 epsilon naught. This is the formula. This is very important result actually. As you can observe here, this electric field intensity is not including any R value. Okay, here no R is there. It means, okay, the electric field due to infinitely charged sheet, infinitely a plane sheet containing n number of charges, it is independent of distance. Okay, imagine this is a plane sheet. Okay, and there are n number of charges are there. If I want to calculate electric field at this point, okay, this distance does not matter for these number of charges. If I consider this distance, no matter, electric field will almost remain same. Actually, electric field is depending on distance, but in such a case electric field is independent of distance. Understood? So 2 points. First point, independent of, I will write here, note, electric field independent of distance, independent of distance. And second point, direction, radially outward. We have considered all the positive charges, therefore the direction is radially outward. If we consider the negative charges, then it is radially inward. Not radially, okay, radially outward, passing through cylinder Okay, these two are the important applications of Gauss law. Next application we shall discuss in next class.